Now we are moving to another section of our syllabus, that is the shell balance approach. So for doing this shell balance approach or shell momentum balance approach, you have to understand certain steps and follow these steps for doing the derivations or problems. So the first step is we have to select a suitable shell of size at a specified location. That means we can explain it with a figure. So suppose that you are given a problem, that is there is a cylindrical pipe and a fluid is flowing through this pipe. You are asked to find out the expressions for velocity distribution and shear stress distribution. So how can you do this derivation? So we can do it by this shell momentum balance approach. That is, the first step is you have to sketch the figure applicable to this problem. So I have mentioned that we are having a cylindrical pipe and the fluid is flowing through this cylindrical pipe from the top portion to the bottom portion. So this is the cylindrical pipe that we have considered, and we have taken the radius of the cylindrical pipe as capital letter R. So we have to find out the shear stress distribution and the velocity distribution for this problem. So the first step is you have to identify a shell of suitable size within the flow area. So that means we know the fluid is flowing from the top portion to the bottom portion. So you have to select the shell of suitable size within this flow area. So this is the shell that I have considered. We are selecting a portion within the flow area. So this is the shell that I have selected. So let us take the flow directions as this is Z and this is R. So we are selecting a shell of suitable size within the flow area. So this much distance, that is the thickness of this shell, we are taking it as delta R. For pipe flow and all, we have to take it as delta R. If in the question it is given that you are considering the flow over a plate and all, you have to take it as delta X. So this is the problem. So first step is you have to identify a shell of suitable size at a specified location. Then the next step is we have to identify the forces that are entering and leaving this shell. You know, there are various types of forces, that is gravity force, pressure force, many types of forces are there. So you have to identify the forces which are entering and leaving this shell. Then the next step is we have to use the steady state momentum balance equation, that is rate of momentum in minus rate of momentum out plus sum of forces is equal to 0. So after identifying the shell and identifying the forces that are entering and leaving and all, you have to substitute this in the steady state momentum balance equation. That is the third step. Then the fourth step is, I told you, if we are having a pipe flow and all, we have to use delta R as the thickness of the shell. And if we are having a plate, the problem is about a plate and all, you have to use delta X. So the fourth step is you have to assume that delta X or delta R, it is tending to 0. So you will get a first order differential equation in shear stress 2. That is, we have already written the expression steady state momentum balance equation. So if you substitute or assume that delta x or delta r is tending to 0. So this will result in a first order differential equation in shear stress tau. And solving that, so along with this, in this differential equation, you will having a constant term also. So you have to solve this constant. So we can solve this constant by using the boundary conditions. So you have to check whether any suitable boundary conditions can be applied with respect to shear stress. So I will tell you about the boundary conditions which are applicable here. So before that, there is 2 more steps. So is the problem that we have considered. Next is step 5. So after using the boundary conditions, we can get the value of the constant and we substitute in the expression for shear stress, and we get the shear stress distribution equation. Then the next step is, depending on the fluid rheology, you have to use appropriate relationships for shear stress and velocity gradient, which result in a second order differential equation with velocity as dependent variable. That means after getting the shear stress distribution or the expression for shear stress, you have to observe the rheology of the fluid. In most of the cases, the fluid will be a Newtonian fluid. So if the fluid is Newtonian, we can use Newton's law of viscosity. That is, mu is equal to tau is equal to minus mu into dvx by dy. Then we are comparing these two expressions for shear stress, and we will get the expression for velocity from this. So first it will be a second order differential equation. After that, you have to integrate and find it out. So while integrating, there will be a constant term here also. So this constant can also be found out by using appropriate boundary condition. So this is a general step or procedure for proceeding with the shell momentum balance approach. And I have told you about the boundary conditions which are applicable. So the first boundary condition is, if in the question it is given that there is a solid liquid interface. So in case of at the solid liquid interface, always the velocity of fluid will be equal to the velocity of the solid. And if the solid is stationary, the velocity of fluid can be equal to 0. This is called as the no slip condition. Here we are assuming that the surface is having infinite sliding friction. So that is the first boundary condition. If you are having a problem with solid liquid interface, you can use the first boundary condition. If the solid is stationary, the velocity of fluid can be equal to 0. The second boundary condition is at the liquid, vapor or gas interface. If we are having a liquid gas interface, then the momentum flux perpendicular to the surface in liquid phase is nearly 0. That means the velocity gradient is 0 at this situation. If you are having a liquid vapor interface, the velocity gradient is 0, or the shear stress is, or the momentum flux is 0. Next is at the liquid-liquid interface. The momentum flux perpendicular to the interface and the velocity in both the phases will be continuous. So these are the 3 boundary conditions which are applicable here. So we can substitute based on the nature of the question given. So you must have a clear understanding about these 6 steps and 3 boundary conditions. Only then you can proceed with the derivations. Okay.